a talk, but a sort of introduction to the main theme of the conference, of course, with some results, sorry. Of course, with some results. So the school is about, as you see, the structure and dynamics of networks beyond pairwise interactions. And the idea is the following. This is also not working. This is also not working. You see, in physics, normally, we tend to distinguish two main class of systems. One is continuous systems. And continuous systems are like fluids, solids. And normally, to model these systems, you use partial differential equations. And then complexity there emerge as a solution of patterns that are generated, bifurcations, and so on. And the most, this is the subject of hundreds of years of physics and statistical physics. One example is Navier-Stokes equation for fluids, where you have turbulence and all this kind of stuff. But then the second class of system you have to deal with are distributed systems. Distributed systems are not continuous. Our systems are made by hundreds, thousands, millions of components, units, that interact. And there the complexity is what? Complexity is the fact that due to the interaction, this unit starts to give rise to a collective motion. And this collective motion can be very complicated, very complex, because it can contain a lot of information. And see, the way normally physicists model these distributed systems is by means of networks. Because you have these units, and these units are the nodes, and you have these connections, and these connections are the links. So the last 25 years, I would say, have seen a revival of network theory, what's called a complex network theory. Network theories, graph theories, long ago. I mean, mathematicians, they know it since the time of Euler. But, you know, in the last 25 years, there have been a revival of network modeling. Why? Because, in a sense, people started to have data with networks from real worlds and the capability of analyzing this data. So they found sort of universal behavior in different networks that characterize the structure and the functioning of this network. So they started a new wave of important studies in network science. Now, where is the problem? The problem is this. There is, however, a strong assumption that is made all the times one adopt a network representation. And what is this assumption? The assumption is that the overall interplay among unitary components, so the way one unit interacts with the rest of the network, is always assumed to be exhaustively described by combination of pairwise interactions. Because a network, a link, is a pairwise interaction. So what you are assuming is that you can describe your system, and the interaction of each unit with the rest is always factorizable as the sum of pairwise interactions. And this is the way that allows you to write a matrix and to model the system, and to treat the system. Now, you understand very well that if the kind of interactions that are taking place in your systems are linear, this is always true. Because if you have a linear interaction and you consider a group interaction with linear formulation, you can always factorize. But when the interactions are nonlinear, like Kuramoto model, where you have sinus of the phase difference, or in the brain, or normally in what happens in real system, then this hypothesis is very short. Because you cannot factorize many-body interaction into the sum of pairwise interactions. And so it comes out that the hypothesis is short and does not represent faithfully these cases. So more and more in the last year, it has been seen from protein interaction network to semantic authorship graph that you have group interaction that you have to take into account in a different way. And this comes then the issue of hypergraphs. It is, these cannot be modeled by network, but they need to be modeled as hypernetworks, where you have units and when you have interactions. And this interaction can be pairwise, 3-body, 4-body, 5-body, and you have to take care of this interaction with the order, the specific order that you have. During the school, we have seen the basic things in mathematics, processes, and dynamics related to this. But this fact has fundamental consequences. I don't want to enter into the issues. So let me make an example. Probably one of the most important issues in complex network theory is ranking. So the fact that networks are not homogeneous. You have more important nodes and less important nodes. And you want to have a rank of the node. No? There are companies making money on this. Google is making money on this. I mean, it's ranking for you. When you make a search, it's ranking for you the web page, so you get in the first indication what you want. It's important to rank proteins in protein-protein interaction because you want to see which is the most important protein, or things with respect to a disease, and these things. So what you do normally when you have a network is you assign to a node a number, a scalar number. It can be centrality, can be whatever, okay? And based on the value of this number, you rank the node. But now, if you have hypernetwork, you see nodes and interactions. This is a pairwise interaction, this is a 3-body interaction, this is a 4-body interaction. You can have situation where each node has different importance with respect to different orders of interactions. Imagine that you have a network. In this network, you have in parallel different processes taking place. And then you can be a node with very high interaction for pairwise interactions. So they're very central in pairwise interaction, but not central in 3-body interaction. So you cannot assign to a node one scalar value, but you have to assign to a node a vector. You have to assign to a node a vector of as many components as the orders of interaction that you have in the network. The first component of the vector will be how central is node I with respect to pairwise. Second component, how central will be with respect to 3-body, and so on and so forth. And the issue is how can you define this vector centrality in a unique way, mathematically. And the way we solved recently in this paper is we pass from a generic hypergraph to the corresponding line graph. Line graph representation is a representation where the nodes are the hyperlinks here. So you see we have 4, 5, 4, 5, 2, 4, 5, 2, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2, 3, 1, 2, 3. And then in the line graph, you set the links. So the line graph is a graph, it's a normal graph. You set the links if there is one overlap between the corresponding hyperlinks. So for example, 1, 2, 3, and 4, 5, they do not have overlap, and therefore there is no this link. Otherwise, you have all possible other links. So this representation is unique. And so now, since this is a graph, you can show that this is a symmetric graph, of course. What you can do, you can use the Frobenius-Perron theorem and extract the vector centrality, the eigenvector centrality of this graph, which is uniquely defined. And therefore, it assigns a value of centrality to each node of the line graph, which means to each hyperlink of the original graph. And then you use this, and with these values, you can define the vector centrality of the node I of the hypergraph in this way. vectors and the non-negative d minus 1 dimensional vector. D is the maximal order of interaction that you have in the network. The component k of this Ci is 1 over k, the sum over all possible elements to all possible hyperlinks of order k of the corresponding value of this centrality in the line graph. So it's uniquely defined, is normalized to 1. But this what does it mean? It means that now you don't have one ranking, but you have d minus 1 ranking. Because now you can rank the node following the value of the first component of this vector, or following the second component of this vector, following the third component of this. So you have different rankings. And the issue is, if I check different ranking, will I find differences? So will I find what I told you before, one node that is very important to one order but not important to the other? And indeed, this is the case. For example, if you take an example that we already mentioned during this call, is the contact person, the contact network. So what you have here is the following. You take this vector, you make this ranking, and then you take, for example, a given subset, which are the top 10 in the ranking, or the top 15, or top, in this case, X. The top X in this ranking. And then the idea is I take the top X ranking with respect to 2 body, 3 body, 4 bodies, 5 body, and I look how much this top list intersect. So if I say big interception means that if I'm very central with respect to one order of interaction, I'm also central with respect to the other. If the intersection is low, instead it means that there is a big difference. And you see that in general there are big difference. This is the situation for the mathematics subset of archive. You have there nodes are authors, papers are hyperlinks, because you have paper with 2, with 3, with 4 authors, with 5 authors, you know. And then what you see is that if you are a mathematician that is very, very famous when you consider 6-body interactions, so paper with 6 authors, you are in general not so famous when you consider other order of interactions. So it means the mathematician tends to have a fixed number of collaborators, okay, in their way of doing. Instead, in contact networks, it's nice because in contact networks, these are other things. These are, for example, composition of commercial drugs. You see that there can be some important overlaps, and in one of them we proved the lower panacea, the hypergraph of contact data. You see that when you are a kid, you know, there is no leadership, so if you are important with groups of few persons, not necessarily you are important in order, but then when you go to adolescent, you have the creation of, there is the nice-looking girls or the sympathetic man, so everybody wants to stay with him, and you have a sort of raise up of leadership, so you are important at one level, but also important at the other. So this is a way that, I repeat, it's important because when you have an hypergraph, this kind of information cannot be extracted, of course, if you have a scalar variable. So you need really a vector variable to discuss a centrality problem. During the conference, we will also have a talk by Charo, which will explain to you how distances changes, how the concept of distances, shortest path, and all other measures related to shortest path, like efficiency, vulnerability, these things can change when you have you pass to hypergraph. Processes, for example, processes, one can say, okay, let's consider games, and let's consider 2 agents, 2 strategy game. You have 2 agents, 2 strategies means you can be cooperator, defector, CD, and normally a game is what? Is a payoff matrix, in which you say how much a cooperator gain when he meets another cooperator, how much it gains when it meets a defector, and vice versa. So you have a matrix. Moreover, if you take the matrix and you write as a function of this parameter st, you can codify all the dilemmas, social dilemmas, the harmony gains, node-free gains, Tagan game, and prisoner dilemma, depending on the values of S and T. And so the idea is you play the game, you accumulate the payoff, and then based on this payoff and on the network structure of connection, you decide which is the next move in the game. And typically, what you do is imitation, for example. So each one of us knows its own payoff, knows the payoff of the connected agents. Say, okay, if Alvaro did better than me, so I say, okay, maybe the strategy of Alvaro is better than mine, and I imitate the strategy of Alvaro. If I do better than Alvaro, I stay with my strategy. And this is reflected by a probability of exchange strategy, which is basically the Fermi probability. No? This is the Fermi probability of having a boson with a given energy when you substitute energies with payoff. Okay? But the idea is that now I can codify, and now I want to define a game on higher order, a higher order game. To define a higher order game, it means that strategies of node I with respect to J must depend on what node K, what the third node is doing. So I have to distinguish the case in which I have triangles in my network as the sum of the three links, and triangles indeed which are fillet triangles, that is, they're representing a real three-body interaction. So the idea is, if I'm playing on a two-body interaction, play I and J, play game one, that is, they adopt values T1 and S1. Okay? When I am here in this situation instead, I have to look what K is doing with I and J. And I have SKI, SKJ, which are the two strategies. I have two options. Either SKI is equal to SKJ, so that means node K is treating me and Charo on the same footing. Okay? Then players I and J, me and Charo, selects T2, S2, and play game 2. Otherwise, if K is not treating us in the same way, we can be jealous. We can be jealous, and then we adopt T3 and S3, and we play a given other game. So the idea what it is, that when you calculate a payoff of node I, this payoff will be the 1 divided the degree of node I, the sum of what node I is doing in each one of the link ij. And on its turn, this is one of the generalized degree of these links, how many triangles are taking place on this link, sum on all triangles tau formed by the link ij of the payoff that node I is doing with j on that specific triangle. And I repeat that if the triangle is open, it's just node 1. If the triangle is closed, it's 2 and 3. So you have a payoff tensor this way, okay? But much more importantly now, if you choose game 2 equal to game 1 and you just change game 3, you see you can put in competition all possible social dilemma. And this competition is ruled by the fraction of triangles which are plenty, because the competition occurs only when the triangle is full. So what you can do is you can choose T1 equal game 1 equal to game 3. You change game 2. Okay, so this, and then you can, depending on T1, S1, and S2, you can define game 1 in harmony gains, Tagant, Snowdrift, and prisoner, and change the order. Now what you do here? Here you introduce a parameter rho, which is the, you imagine, first of all, you generate a network with all triangles. And then you have a parameter rho, which is the density of triangles which are real triangle, three-body interactions, not two-body interactions. So rho equal to 0 means that you are in the normal case. Normal case, you play just node 1 on a network. Rho equal to 1 means that you are in a fully three-body case with no two-body interactions. But when you have rho in between, you have, half and half. Some of interactions are two-body, some of interactions are three-body. And what you observe is that when you put in competition these different social dilemmas, which, by the way, have different Nash equilibria, because the harmony game has full cooperation, prisoner dilemma has full defection, and the other one has mixed state, all the times when you change your rho, you pass from full cooperation to full defection or vice versa. So you can determine a transition between one Nash equilibrium to the other Nash equilibrium, changing the fraction of higher order interaction games. But what is much important here is what happens close by to this transition. That is, what happens in the region where here you see white. Okay? If you put yourself there, that means you have a balance between two-body and three-body of that case, what you observe is this. So, here and there you have either the system fully cooperating, for defection 0, cooperation 1, or the system with the opposite, defection 1, cooperation 0. But if you are there, you see that the system has sets in a non-stationary state, asymptotic but non-stationary state. What does it mean asymptotic? That the state continues forever. Continues forever and never goes to a constant. It's asymptotic and it's non-constant, where the system alternates period where the majority of agent is cooperating, to periods where the majority of agents is defecting, then again cooperation, then defection, then cooperation and defection, then cooperation and defection, which is, if you think what is really happening, because the stupidity of these games is that once you get to the Nash equilibrium, you are frozen. So this means that if these games would be really modeling what happens, that means you are destined to be either forever a cooperator or forever a defector, depending on the Nash equilibrium where you fall. But normally what is I'm and Hernan cooperates because we are friends. When we have, then we choke and then we defect. Then we make peace and cooperate again. This is the idea. And this state, which is inherently prohibited for pairwise games, immediately gets in when you consider higher order interactions. So you see, higher order interaction, not only they produce a much richer dynamics, but they introduce some dynamical states which are even prohibited for pairwise interaction alone. Okay? So this is a nice example. Again, this was published by Haas in 2021. Then, how much time I have? Another 10 minutes. 10 minutes. This is what I also described in the school, the fact that you can treat synchronization. But now synchronization when nodes are represented by a vector xi, a state vector xi, which, as a function of time, has a local evolution f, which tells you what the system is. It's a Lorentz, it's a Rössler, it's a Mackie-Glass, it's whatever. And then you have pairwise interaction, three-body interaction, blah, 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 d plus one body interaction. Consider simultaneously each order of interaction that corresponds to a given interacting strength times the sum or the double sum or the sum of what? Of elements of the adjacency matrix, adjacency tensor, adjacency hypertensor, blah, 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 times some function, G1, G2, Gd, which are function of d variables at level d, which tells you the interaction of these things. And this is the most complete way you can write interaction of dynamical system in an hypergraph. And then I go fast here. You have the details in a paper which just was published at that time when I prepared the slides, was in preparation, but now it's published in Nature Communication. When all the coupling functions are synchronization non-invasive, that is, when GD of x6666 is equal to 0 for all D, then you can show that you can introduce generalized Laplacians. The linearized equations are this way, and they depend on the Jacobian of f, Jacobian of G1, Jacobian of T2, times these generalized Laplacians. And each of these generalized Laplacian can be diagonalized with the different bases, so you have all the mapping of one base into the other, so you can use the base, for example, of pairwise interaction as a reference, and you can map everything there, and then you get some nice prediction. For example, this is what happens for Rössler system and Lorentz system, and you look at here, this was one of the questions we had during the school. Can the master stability function oscillates? This is the case. Okay, so, and of course, as you see, the interaction here is non-linear, because otherwise, if it is linear, it's just factorizable. Okay, so I repeat, this is just the results. So if you are interested in, you can read the Nature Communication paper that was done. Last but not least, what happens in the Kuramoto model? Kuramoto model is another example of non-factorizable interactions. Is a very simple equation where you have the phase of node I, theta I, is equal the derivative in time, a frequency, omega I, plus the interaction with the rest of phases, which, as you see, is the sinus of the phase difference, proportional to the sinus of the phase difference. So all nonlinearity is here. By the way, Kuramoto is the one who won this year the Boltzmann Prize. So very soon in Florence, in Stadtfest, they will give him the Boltzmann Prize exactly for writing this equation here, which had tremendous application, thousands of papers on these things. Now, of course, this is a pairwise interaction, but then you can extend this to a diffusive coupling in three-body. No? Here, it's theta k plus theta j minus twice theta I, because it means theta k minus theta I plus theta j minus theta I. With the only difference that the sinus of is different from of. So it's not linear. You cannot factorize. You can make another extension of this model in a d dimension. That is, you can take a vector. This is what? This is a phase. So it's a point on a unitary circle that is going around. So a point in a unitary circle can be has coordinates in the plane cosinus theta I, sinus theta I. You can take this point, write an equation for this vector, which is this. And then you immediately realize there's no reason to stay in 2 dimensions. You can stay in 3, 4, 5, 6, 7, 8, 9, any dimension. The only important point is that the sides, I mean, this vector be normalized to 1. Huh? So you can study with the same model how phases are rotating in a circle, the classical Kuramoto, but you can also study points which are moving on the surface of a sphere and how they orient their position, which is flocking. Because the birds have a velocity and they orient their direction in 3D. But you can also have how you can have alignment on points that are moving on a hyperdimension, a hypersurface, whatever you want. Okay? So you can make these two extensions. If you are interested, we have several papers here. What is nice is that if there is a fundamental difference between odd dimensions and even dimensions, which is obvious because if you have an even dimension, R3, R2, R4, R6. R4 is R2 times R2, so you have two phases. R6 is R2 times R2 times R2, so you don't change the essence of the Kuramoto. You simply have two independent phases, and you have to adjust them. Whereas if you are in odd dimension, this is not true anymore. You have an axis of rotation. In the Earth, you have the axis. So if you prepare initial condition, the North Pole, this initial condition stays there forever. The nodes are moving on parallels of this thing. So, and this determines that the transition to synchronization, in one case, is continuous, in the other case, is discontinuous. Okay, so in one case is second order like, in the other case is one order like, first order like. And this complicates even more when you put higher order interaction, because this can be also doubly discontinuous. But much more important is this. If you consider in the Kuramoto model higher order interactions, you get the possibility of having partially synchronized situations, so states with a non-zero value of the order parameter for negative values of the coupling strength. Now, for the people who are expert in Kuramoto, there is a fundamental paper by Steve Strogatz that says that the necessary condition in Kuramoto to have synchronization is to have at least a portion of oscillators which are positively coupled to the mean field. And he proved this, and in this case, if you have all your oscillators which are negatively coupled to the mean field, so this state cannot exist, once again, in pairwise interactions. It really cannot exist. It's prohibited, it's forbidden. But you have three-body interactions, then you have a different closure of phases which you can create synchronized states also for negative coupling. And you see this was published by PRL, by us. It says contrarians synchronize beyond the limit of pairwise interactions. So this is just a flash to tell you that these higher order interactions are not just a mathematical, so to say, complication. They really play a role. They enrich the dynamics of networks. They introduce new states. States that are prohibited when you don't have them. States which are really forbidden. So during this conference, I hope that the presentation of all the speakers will also enrich the discussion. And this higher order interaction, in my opinion, really opened a new trend, a new field, a new interest to networked system, to distributed system. This is a list of possible things. Of course, I concentrated on my contributions. There are many other groups doing this. If you are interested on synchronization, there are two thesis reports. One I wrote in 2002, and then there is also a book I wrote, Network Dynamical Systems. This is the paper that discusses, the structural issue, the vector centrality. This is the paper that discusses evolutionary games. This is the paper published in Nature Communication that discusses the master stability function for synchronization in simplicial complexes. And this one, the last two, discuss other dynamical state occurring in network beyond pairwise interaction. So said so, thank you a lot, and I'm open to any question you want.
Thank you very much. So we have time for questions. So I hope you have questions.
Hernan.
All right, yeah, very nice talk. I enjoy a lot. So, you treat the case of diffusive couplings, right, and leading to complete synchronization.
Yes.
And so I just wonder if there is any treatment for the problem of cluster synchronization on hypergraph and simplicial complexes. Is there anything done
Okay,
along
so-
that, going from complete to cluster synchronization?
Okay.
Uh-huh.
There is a complete solution
Hmm.
of cluster synchronization for diffusive coupling, for synchronization non-invasive coupling. It's another nature communication we have done this year, so you can describe all possible clusters that I shown to during the school.
Still with diffusive coupling, right?
Is still with synchronization non-invasive coupling.
Non-invasive coupling. So, but suppose that the couplings are non-invasive.
That's, you have nothing.
Nothing.
No, that's a very important question now, seriously. If the coupling is synchronization non-invasive, diffusive is one possible coupling, which is synchronization non-invasive, then the solution is, under one approximation, is practically done. I will send you the paper. What happens when the synchronization, when the coupling is synchronization invasive, that this is not zero? It happens that when you change sigma, the coupling strength, you not only change the stability of the solution, but you change the solution. Because the solution is not invariant with respect to sigma. So you are modifying the shape of the solution together with its stability. And so you cannot separate these two things. That's why it's extremely difficult, and to my knowledge, no extension of the master stability function has been done to generalized synchronization, because it's a sort of generalized synchronization. It's not synchronization on, on the hyperdiagonal. It's on the some strange manifold, and then this has not been done. It's a very interesting question because, for example, in the brain...
Well, I guess that in biology, it's all about cluster synchronization, right? It rarely happens that you have an entire brain. Well, if you have a seizure or if you have some particular state. Yeah.
So what I'm telling you, if the kind of interaction is Kuramoto, for example. Kuramoto is a synchronization non-invasive because it's sinus of the phase difference. So when the phase are equal, sinus of 0 is 0.
You have a solution.
So you have a complete solution of clustering of Kuramoto.
And then you work from there.
So then you tell me, hey, but Kuramoto is also neurons because you put the flag. Okay, then you have everything. Okay? But then if you want to really study Hodgkin-Huxley equation with the real synaptic, then this is synchronization non-invasive. Invasive, sorry.
Invasive, yeah.
And there is no...
No, nothing. Okay.
Nothing yet.
Thank you.
Are there...
Thank you for your presentation. Could you explain again the graphics that you show about mi of x?
About?
Mi of x. There's a mi with
mu of x.
Yeah. Yeah, there's one. Yeah.
Yes.
So what is C, Cy, and Cj?
Ci, Cj is, you see, different components of the vector of centrality vector. So take component I, component j. That is order I, order j. No? These two components furnish you two different rankings. The ranking of the nodes following component I, the ranking of the nodes following component j. Then you take the top of these two lists. The top x nodes. The first 10, the first 15, you decide. And then, okay, mu x, Cij, is the fraction of the overlap between the list of the top x node ranked with Ci and Cj. So mu is high when in the two top nodes you have the same nodes in the two top list. It's low when the top list of I is done with some nodes and the top list of j is done with some other nodes. So it means that if you are important with respect to component I, you're not important with respect to component j.
Okay, I never understood. Thank you.
Nuno.
Thank you, Stefan. One question regarding the contrarians. on the Kuramoto model.
Yes.
First, the way you define contrarians is by having a negative prefactor, right? Like
Yes.
in the pairwise interaction.
Yeah, the way contrarians was defined by Strogatz is you take Kuramoto, and in Kuramoto you have an all-to-all coupling normally. Now you define two populations, the contrarians and the conformist. You know, Stephen Strogatz is fantastic with words. No, I told you, conformist, contrarians. So, you have to do like this, novelist. So contrarians and conformists. So the conformists are those which are positively coupled, in the sense they are conformists because we are going with the mean field. And the contrarians, the one who oppose the mean field. So then he demonstrated if you put and then you have, so you say that of your population P, fraction P is contrarians, 1 minus P conformist. If you take fraction P equal to 1, it demonstrates no synchronization. Then what it's doing is taking fraction P equal to 1, and then progressively switches 1 contrarians into conformist. Okay? So, and it can do it randomly, following the degree sequence, following the anti-degree sequence. You can do whenever you want. And in all cases, what you see is that in order to have the switching of synchronization, you need to have a finite number of contrarians larger than a given threshold. So the statement is that the necessary condition to have synchronization in classical Kuramoto is that at least one fraction, non-negligible fraction, in the thermodynamic limit of oscillators have to be positively coupled with the mean field. Not all. It's not necessary that all of them are, but one fraction larger than a given threshold. And what we have shown in this paper is that if you now switch on the higher order interactions...
But my question is, if you keep the two-body interaction, or...
we did also this, and you have a region...
You need to keep the two, right?
Yeah, you have a region. You have a region because now you have not only lambda, but you have lambda 1 and lambda 2. And so you have a region in which both lambda 1 and lambda 2 are negative. So in this case, you can push also.
Okay. Because the idea is that you have at least a triangle, right? And so you have the frustration that comes from the topology fighting the
so
one that
easy. What happens here, if you look at the paper, is that normally synchronization, the Kuramoto is the formation of one cluster because you have one fixed point. No, here is two clusters because the phase and antiphase slightly turned. They're not exactly phase and antiphase. There is a little bit mismatch here, and so you have that. All the entire system is completely ordered. Half of the nodes are in one phase, and half of the nodes are in the antiphase with this minus a little bit of phase. And this minus makes that you have a R different than 0. Because if they were half and half, one in phase, the other antiphase, they would cancel, and R will be 0. No? Okay. So you have to go there. It's really a different collective state. And now we are extending to 5 or 5th order, frustration, blah, blah. So, but there is really a new world of phenomena that happens in Kuramoto.
Are there other questions? Stefano, is it possible to formulate this Kuramoto in a different way?
In the little?
In a different way. Instead of sine of the sum minus 2 theta I or something, make it in different way.
In which sense? Different way?
For instance, sum of two sines.
Yes, you can do whatever. This is the... If you sum two if you take sinus this plus sinus this, then it's factorizable. You have to find something that is not factorizable. Something that you cannot write, you cannot disentangle into the sum of something. Otherwise, you just renormalize the elements of the adjacent symmetrics, and you get a different network, weighted network, with this renormalization. But the idea of real, and this be warned, because now higher order networks are very fashionable. Everybody writes high order, high order, high order, high order. It's like, artificial intelligence, everybody. And there is a lot of shit here. A lot of papers that say this is high order, this is high order, but then you see that you can factorize, and it's really an idiotic point. So the point is you have to be careful that the real high order interactions in dynamics are those which cannot be factorized into the sum of. Otherwise,
in this last transition you show, can you measure a kind of a susceptibility?
what do you mean associativity here?
Fluctuations.
Fluctuations. We didn't do, but probably yes, and could be interesting. Yes, why not?
To understand the kind of transition you have.
Yes, yes. Yes.
Okay. So if there are no more questions, let's thank IUF.
Another one.
Sorry.
I am just confused with the representation of high order network. So I can represent that as like ordinary adjacency matrix and just find the point that everyone is connected, or I need to propose a high order adjacency matrix.
No. So the representation is an hypergraph. You have points and group interactions. But this is as soon as you stay in mathematics. When you go to processes and dynamics, you put process and dynamics, you have to define the interactions. And this is the idea of non-factorizable. Simply this. Okay? Because if they are factorizable, it's just you can change representation and you stay back to the case of network.
So if my subject can be studied at factorized networks, I cannot truly apply high order.
Which one?
My subject. Where I studied neuroscience.
Neuroscience. Neuroscience, there are several problems. I mean, okay. Something you can do, for example, synchronization you cannot apply because what we said before. Most neuronal systems have interaction, not that they're not factorizable. They're not factorizable, but they're not zero in synchronization manifold, and that's a fundamental assumption of the model. So something you can do, something no.
Okay.
Maybe he has some extra. No, please. What? Okay, question.
Yes, very, very quick. The extension to D-dimension of Kuramoto. When you said on the sphere, how precisely do you define a sphere in higher dimensions?
It's no. What you have is that the condition is that the norm of this vector be 1, or if you want, constant. So this defines a sphere or an hypersphere.
Yeah,
because it's the radius which is constant.
Yeah, because when you go for in more than 3 dimensions, you end up having 3 different ways in which you can define a sphere.
The idea, for me, a sphere is just the fact that they move on a surface such that the norm of the vector is constant.
Okay, so topologically, perfect. Thank you.
Okay.
Okay, let's thank the speaker again.
So let's take also the chairman and and Alvaro that is leaving. So now we move to the first serious talk. Mine was not serious. And the serious talk is